In this video, I'm going to explain the difference between a continuous function and a uniformly continuous function. So before that, let me recall the definition of a continuous function on R. It is defined in this way that if for every point C belong to R and for a given epsilon greater than 0, however small it is, there exists a delta greater than 0 such that for every x belong to R with mod x minus c less than delta, we must have mod fx minus fc less than epsilon. That means when x lies in this interval, mod x minus c less than delta means what? Means that it is greater than minus delta but less than delta. And this will implies that c minus delta will be less than x less than c plus delta. That means for every x lying in interval c minus delta to c plus delta, the value of f mod fx minus f of c should be less than epsilon. Now here also mod fx minus fc less than epsilon means the same thing, that f of x lies between f of c minus epsilon and f of c plus epsilon. So within this range, c minus delta to c plus delta, f of x should lies between these 2 points, fc minus epsilon and f of c plus epsilon. Now let us consider this particular function fx is equal to 1 by x for x belong to open interval 0, 1. As we all know that this one is a continuous function, and the graph of this function is presented by this brown colored pen here. So this is the graph of fx is equal to 1 by x. Now here you see that if I take this epsilon to be this much, the length from here to here, then take a point A here. Now this delta, by considering this delta to be this much, then for this point A, this particular delta work. That is, if I take any point within this range, A minus delta to A plus delta, then the value of fx will lies between f of a minus epsilon and f of a plus epsilon, because you can see from the graph that since this graph lies inside this one, and if you take the distance of any point from take any point on this graph which lies inside this rectangle, then you'll see that the value of fx will always be within this range f of epsilon, f of a to fa plus epsilon. And if I take a point somewhere here, then it will lies between fa minus epsilon and f of a. So you see that for this particular epsilon here, and for this point A here, this particular delta works here. But now if I take the point B, which is another point on this graph of y is equal to 1 by x, then you see that the same epsilon will not work the same delta will not work. By considering the same epsilon and the same delta, you can see that if I take a point here, this point lies still within this range of b minus delta, b plus delta. Because if you drop a perpendicular, you can see that it is still inside the rectangle, this rectangle whose length is twice delta and breadth is twice epsilon. But now when you take the value of this point here, what will be the value of this point? Suppose this is say b1. Then f of b1, you can see that it lies outside this rectangle. So that means the same delta will not work in this case for a given epsilon. That is, for a fixed epsilon, then this same delta will not work, but at point A, this delta work, but at point B, this delta does not work. So in that case, you see that this delta not only depends on epsilon, but it depends on the choice of a point C also, point on this graph. So here you see that if I reduce this length of delta, if I take this one, reduce it, then in that case you'll see that with the same epsilon, but I reduce the value of delta, say delta 1. Then you see that in this case, for the given epsilon greater than 0, this delta 1 now work for this point B. So you see that for different points here, the same delta will not work for a given epsilon. And in this case also, you can see that if I take another point here, then with the same epsilon, this value of delta given the value of delta that I have chosen for point A and point B will not work in this case. I have to reduce this value of delta to this much so that you see that whatever points I'm taking here, then the value of f of that point will still lies inside this rectangle, which is represented, if I take this one as C1, this point here as C1, then this will be f of C1 plus epsilon, this will be f of C1, and this point here will be f of C minus epsilon. So you see that for the same epsilon, you have different values of delta that will work for different points. So now this is the definition of a continuous function. That means for every epsilon, for every point C and for every epsilon C, for every point C and for every epsilon greater than 0, there must exist a delta greater than 0 satisfying this condition. So you see that for point A we have this delta, for point B we have this different value of delta 1, and for point C we have another value of delta. But since we are able to find for every point which satisfy this delta, which satisfy this condition, then this is a continuous function. Okay. So now you see in this case, in this particular graph, we see that delta depend on the choice of point. Not only an epsilon, but on the choice of points. But now I'm going to show you another graph where delta depend also on the, this is another example where delta depends on the choice of point. With the same epsilon here, the length from here to here, the length from here to here will be that one, and the same delta. This will not work because for this particular point, you see that since this graph lies within this range, say a minus delta to a plus delta, and if you take any point here and the value of f of that point will still lies inside this rectangle. But in this case, you see that if I take a point here, this point, which still lies inside this range, say suppose this is point C, then it will be f of C, it will be C minus delta, C minus delta, C plus delta. So for this point C, which still lies inside this range, C minus delta to C plus delta, the value of f of that point, for example, if I take it as C1, this one as C1, then what is f of C1? F of C1 will be this one. F of C1 will be outside this rectangle. So in this case, you see that the same delta does not work. So this is another example of the graph where delta depends on the choice of points. But now I'll show you that delta depends on epsilon also. So you can see from here that how delta depends on epsilon. By considering this graph, you can see that in this case, at this point, if I denote this as point A, if I take this epsilon to be this much, the length from here to here, then, and I'm considering this delta to be the length from here to here. So now you see that in this rectangle, whatever points you choose here, then in that case, the value of that f will not be in, within this range. You'll see that the value of f will be still lies inside the rectangle. But now if you take this point which still lies inside the interval a minus delta to a plus delta again, then you'll see that the value of f will lies outside the rectangle. It will be this one. And then if I take another point here, then you'll see that it is still lies inside this rectangle a minus delta to a plus delta, but the value of f at this point will be no more inside the rectangle, but it lies outside the rectangle. So in this case, you see that this delta does not work, so for this given epsilon. But now let us take this one. If I consider this epsilon to be this much, then in that case, you see that if I increase the value of epsilon, then you'll see that the same delta will work in this case. Why? Because you see that if I take any point which lies inside this, if I take this as point B, B minus delta to B plus delta, that means in the interval B minus delta to B plus delta, whatever point I select from here, then the value of f will still lies inside this rectangle, because here I've increased the value of epsilon. So you see that delta depends on the choice of epsilon also. Now for a given epsilon, if I take it as a if I decrease the value of epsilon, then in that case the same delta will not work. But how when I increase the value of this epsilon here, then the value of delta work for this particular point. So this is an example. This is an example where delta depend on epsilon. So now what we notice is that for a continuous function, we see that delta not only depend on the choice of a point C and a point C, but also depend on epsilon. But now in the case of uniformly continuous function, let me define first the definition. F is said to be uniformly continuous on R if for every epsilon there exists a delta. Here is not for every point C belong to R and for a given epsilon greater than 0. It is defined in this way: if for every epsilon greater than 0, that means if for a given epsilon greater than 0, however small it is, if you can find a delta greater than 0 satisfying this one condition, that for every x and y belong to R, with the condition that mod x minus y less than delta, then we must have fx minus fy less than epsilon. Now mod x minus y less than delta will implies that x minus y is greater than minus delta less than delta, and this will implies that y plus delta, then x is less than y plus y minus delta, this is y plus delta. Then mod f of x minus f of y less than epsilon will implies that f of y minus epsilon should be less than f of y less than f of x less than f of y plus epsilon. So that means the value of fx or f of y should lies fx should lies between fy minus epsilon and fy plus epsilon whenever x is lies in this interval y minus delta to y plus delta. So in this case, in the case of uniformly continuous function, this delta depends only on epsilon, not on the choice of point C. So by taking this function, consider this function, y is equal to x or fx is equal to x. As we all know that this is a continuous function, so let me define it in this interval, say 0 to 1. So now this is a continuous function. So now for a uniformly continuous function, the same rectangle will work. That means for a given epsilon greater than 0, however small it is, we must be able to find a delta greater than 0, which depends only on epsilon, such that that same rectangle, here you see that if I am taking this epsilon to be this much and delta to be this one, then this rectangle, you can construct a rectangle. Now this same rectangle will work for this point also. If I take this point as A, this as B, then you see that if you bring it here also, then it will work. If you take shift this rectangle to this point also, then in that case it will work, because you see that for a given epsilon greater than 0, whatever be the value of epsilon, however small it is, and there will always we can always find a delta which will satisfy for every point on this one. Every point on this graph of y is equal to fx. That is, if I take any point here, say this is x and this is y, then what is f of x? F of x will be this point which still lies inside this rectangle, and what is f of y? It will be this one. And you see that the difference of these two will be still inside this region or inside this rectangle. So what we notice is that in the case of uniformly continuous function, the same rectangle work, or for a given epsilon greater than 0, however small it is, we can find a delta which will work for each and every point in the interval, this one. of this interval 0, 1 in this case, okay, for this particular function y is equal to x. So you see that in this particular case, for a function y is equal to fx, y is equal to x, we can always find a delta which will work for every point in this interval 0 to 1. So this implies that the function is uniformly continuous. Okay, by definition, if we can find a delta which depends only in epsilon, then in that case it will be uniformly continuous. But in the case of a continuous function, the delta depend not only on epsilon but also on the choice of a point for which mod x minus c less than delta will always implies mod x minus f of c less than epsilon. Hope it is clear now regarding the difference of this one, the difference between a continuous function and a uniformly continuous function.